While the classical mass-on-spring model can provide important insight, it is not sufficient to explain all aspects of spectroscopy. Therefore, we have to turn to quantum mechanics, and I will start with a reminder of quantum mechanics. But first I want to give a motivation for presenting the theory. Spectroscopy aims at obtaining molecular information on the system under study. The link between experimental observation and the obtained information is provided by theory, in particular by the theoretical description of the interaction between electromagnetic or particle radiation and matter. So theory turns the observed effects into valuable information about the system of interest. The general principle in spectroscopy is the following. Electromagnetic radiation perturbs molecules or atoms, and this makes them change their state, which implies that they lose or gain energy. The theoretical challenge is to predict whether the effect is strong or weak, and why this happens only at certain wavelengths. This can be best done in the framework of quantum mechanics. Fundamental will be the description of energy levels of a molecule and of the interaction between radiation and matter. Therefore, we will review some important concepts in quantum mechanics in the next few minutes. The state of a system, which can be an atom or a molecule for example, is described by a wave function or by a state vector. Wave functions are used in the position representation of the general theory and are often named psi. More generally, the state of a system can be described by a vector, called state vector, in a multi-dimensional vector space, called the Hilbert space. State vectors will be indicated by the vertical bar in the angle bracket according to the Dirac notation. Expressing quantum mechanics in terms of wave function or state vector are two equivalent forms of the theory, and we will use both. A quantity that can be observed in an experiment is represented by an operator. So we have operators for energy, dipole moment, location in space, velocity, spin, and so on. A famous example is the Hamilton operator H for the energy. Operators are indicated by bold print in this course. An operator acts on state vectors and alters them. For example, H psi represents the effect of an energy measurement on the state vector psi. The result is a new state vector that is in general different from psi. Often the experimental values can adopt only particular discrete values. For example, many energy measurements give only certain energy values. In other cases, the measured values are continuous. For example, when the position of a particle is measured. When an experiment is repeated, like an energy measurement, the result is generally not the same, but the values scatter around an average value. This irreproducibility is an inherent property of the quantum mechanical theory. What is reproducible is the average result of the measurement. This average value can be computed by calculating the so-called expectation value of the operator that represents the observable being measured. For example, this expression is the expectation value for the energy. Psi, H psi, is the scalar product, also named the dot product, between two vectors, the vector psi and the vector H psi. The latter one is the vector that is obtained after H operates on psi. The scalar product is zero when the two vectors are orthogonal. It is maximum when the vectors are parallel. Representing the state of a system by wave functions, the expectation value is the integral over all space of the conjugate complex of psi times the Hamilton operator and the wave function psi. In special cases, an experiment always gives the same result. Then the system is in an eigenstate before and after the measurement. More precisely, the system is in an eigenstate of the operator that represents the observable being measured. For example, if an energy measurement always gives the same result, then the system is in an energy eigenstate. In other words, it is in an eigenstate of the Hamilton operator. And the result of the measurement is the energy of the system. If the system is in an eigenstate of the Hamilton operator, then it remains in that state for infinite times. One says that the state is stationary. That means it does not change with time. No transitions to other states are possible. However, transitions between energy eigenstates are fundamental to understand spectroscopic experiments. How does this fit together? In order to induce transitions, the system needs to be perturbed. The system can, for example, be a molecule. The Hamilton operator of the isolated molecule describes the energy contributions and interactions within the molecule. It does not consider interactions with the environment. The system is unperturbed. However, when electromagnetic radiation hits the molecule, it will interact with the charges and magnetic moments of the molecule. This is an example for a perturbation. This interaction changes the energy of the system, which means that the Hamilton operator for the isolated molecule is no longer an adequate operator to describe the energy of the interacting molecule. Instead, the Hamilton operator of the perturbed system consists of the original Hamilton operator H and a perturbation operator V. Since H is no longer an appropriate Hamilton operator, its eigenstates are no longer proper eigenstates of the perturbed molecule. Still, they are in many cases good approximations of the real eigenstates, and it is easier for us to use them also in the description of the perturbed molecule. If we do so, the perturbation induces transitions between the eigenstates of the unperturbed Hamilton operator, for example, between the eigenstates psi0 and psi1. Psi0 is the ground state of the unperturbed molecule, and psi1 is an excited state of the molecule. The perturbation V may induce transitions from psi0 to psi1. The probability for a transition is given by Fermi's golden rule, which is one of the few equations that I want you to remember. Fermi's golden rule was discovered by Paul Dirac, but named golden rule by Enrico Fermi. That's where the name comes from. According to the rule, the probability for the transition is proportional to the squared absolute value of the scalar product of the vector psi1 and the vector psi0 under the influence of the perturbation operator V. Before discussing this expression in more detail, I want to show the expression of the golden rule in the position representation. Here, this scalar product is written as the squared absolute value of the integral over all space of the conjugate complex of psi1, the perturbation operator V, and the ground state wave function psi0. An interpretation of the golden rule is straightforward in the Dirac notation. The figure shows three vectors: the state vector of the ground state psi0, the state vector of the excited state psi1, and the state vector of the perturbed ground state V times psi0. Note that orientation and length of the perturbed ground state vector v psi 0 are different from those of the unperturbed ground state vector. This is important. It says that the perturbation changes the state of the system and produces a new state vector that is different from the ground state vector. Note also that the two eigenvectors of the Hamilton operator psi 0 and psi 1 are orthogonal. The scalar product or dot product psi 1 v psi 0 is a projection of the perturbed ground state vector v psi 0 on the excited state vector psi 1, as shown in the figure. It analyzes how similar these two vectors are. The projection is 0 if the two vectors are orthogonal. It is maximal if they have the same direction. An analogy is the calculation of, for example, the y component of a vector in three-dimensional space. The y component is the projection of this vector on the y-axis. In other words, it is the scalar product of the vector and the unit vector along the y-axis. If the perturbation v has no influence on psi 0, then the perturbation operator v does not change the ground state vector. Therefore, the vector v psi 0 is the same as psi 0 and is orthogonal to psi 1. The scalar product, which is evaluated in Fermi's golden rule, is 0 and no transition occurs. A transition will only occur if the perturbation makes the initial state psi 0 somewhat similar to the final state psi 1. That means if v psi 0, if the vector v psi 0 is rotated away from psi 0 towards psi 1. Summary. Transitions between energy eigenstates can only be induced by a perturbation of the system, which is, for example, a molecule. The probability of a transition depends on the degree to which the perturbation distorts the initial state of the system so that it becomes more similar to the state after the transition. When we discuss spectroscopic methods, it will be important to identify the perturbation and the relevant eigenstates of the system. We will return to the eigenstates when we discuss the different spectroscopic methods, because the relevant eigenstates are different for different methods. On the other hand, the perturbation operator V will be the same for most methods considered in this course and will be further discussed in the following. So our strategy in the following will be to specify the perturbation operator and to apply Fermi's golden rule, but to leave the state vectors psi 0 and psi 1 unspecified. The state vectors may represent any initial and final state. Even if you have been exposed only little to quantum mechanics before, you should not worry too much about the details of the calculation, but you should try to get the concepts. So what is the perturbation V? It turns out that for most of the methods in this course, the interaction of the molecule with the electric field E of the electromagnetic wave is most relevant. As we have already seen, the electric field of the electromagnetic wave interacts with the partial charges of the molecule. To simplify things, we describe the distribution of partial charges simply by the dipole moment of the molecule. Then the interaction is between the electric field and the dipole moment. Classically, the interaction energy between a dipole and an electric field is this expression, which is the scalar product between the dipole moment vector and the electric field vector. The lines above the symbols indicate the vector nature of the quantities. By analogy, the interaction energy operator between a molecule and light is given by the same expression, where V and μ V and mu are operators that describe our molecule of interest. E is the oscillating electric field vector of the electromagnetic wave. We return now to Fermi's golden rule. The dot product psi1 V psi0 contains two vectors. The vector that is generated by the action of the perturbation vector V on the initial state vector psi0 and the final state vector psi1. The dot product is a projection of these two vectors on each other. It analyzes how similar these two vectors are. The projection is zero if the two vectors are orthogonal. It is maximal if they have the same direction. If the perturbation V has no influence on psi0, then the perturbation does not change the initial state vector, and V times psi0 equals psi0. The scalar product psi1 V psi0 becomes then the scalar product between psi1 and psi0, which is 0, since both vectors are eigenvectors of the Hamilton operator and therefore orthogonal to each other. Only if the perturbation deforms the initial state psi0 so that it somewhat resembles the final state psi1 will the scalar product psi1 V psi0 and the probability for the transition be different from 0. When we insert this perturbation potential into the expression for the transition probability, we obtain this expression, where we can extract the electric field from the scalar product because it does not act on the eigenstates of the system. Only operators do that. Both the term on the left, this one, and the electric field are vectors. But why is the term on the left a vector? This is because the dipole moment operator has three components, one for each direction in space. So the term in brackets represents actually three scalar products, one for the x direction, one for the y direction, and one for the z direction. In other words, the term in brackets is a vector. So when we evaluate this expression, we have to consider the direction of the vectors and have to multiply their length with the cosine of the angle between them, which I have named alpha. With this, the transition probability becomes proportional to this expression. Thus the scalar product psi1 mu psi0 and its squared absolute value determine the transition probability. They are therefore fundamental quantities in spectroscopy and have been given names: transition dipole moment, or transition dipole, and dipole strength, or oscillator strength. Both are quantities that entirely depend on the molecule and on the initial and final states. As we have seen in the equation above, this one, the probability for a transition depends also on the angle alpha between the transition dipole moment and the electric field vector. The probability is large when both quantities are parallel or antiparallel, but 0 when they are perpendicular. The transition dipole moment between the ground state and the first excited state is often abbreviated μ1 0. It is written like this in the Dirac notation and like this in the position representation. The most common unit of the transition dipole moment is debye. It is a unit in the CGS system, and the corresponding unit in the SI system is coulomb times meter. Here's debye, and here's coulomb times meter, and the conversion factor is given here for completeness. The transition dipole moment has the same unit as a classical dipole moment. As the classical dipole moment, it is also a vector. Dipole strength d10 is the squared absolute value of the transition dipole moment. It is proportional to the transition probability and therefore also to the integrated absorption coefficient epsilon, which is the area under an absorption spectrum. The Einstein coefficient A for spontaneous emission and the Einstein coefficient B for induced absorption or emission are also proportional to this quantity. There are several misconceptions of the transition dipole moment. It is neither the dipole moment of the ground state, which would be psi0 mu psi0, nor is it the dipole moment of the excited state, psi1 mu psi1. In these cases, we have the same state vector on both sides of the dipole moment operator. In contrast, we have different state vectors in the expression for the transition dipole moment, psi1 and psi0. Sometimes one finds in the literature that the transition dipole moment is the difference between the dipole moments of the two states. But this would be psi1 mu psi1 minus psi0 mu psi0, which is different from the expression for the transition dipole moment. Therefore, this interpretation is also wrong. So I would like you to remember that dipole moment and transition dipole moment are different quantities. They should not be mixed up. So what is the transition dipole moment? The transition dipole moment is a quantity that connects two states, psi0 and psi1. It is therefore a property of the molecule and of two of its states. Different transitions of the same molecule will in general have different transition dipole moments. In contrast, the dipole moment is a property of one particular state, for example of the ground state. This shows again that dipole moment and transition dipole moment are different. Since mu is a vector operator, the transition dipole moment is also a vector, having a fixed direction relative to the molecule. Its alignment with the electric field of the electromagnetic wave determines the transition probability as shown here. The figure on the right shows transition dipole moments for different transitions of N-alkyl adenine. The transition dipole moments for the transitions at 207 and 240 nanometers lie along the long axis of the molecule, and that of the 260 nanometer transition nearly perpendicular to it. Each transition dipole moment is shown with a double arrow here and there, because its absolute direction cannot be determined experimentally. The reason for this is the oscillating electric field, which points in opposite directions during one oscillation. This makes that only the relative alignment between electric field and transition dipole moment can be probed, but not the absolute direction of the transition dipole moment. In other words, the absolute direction of the transition dipole moment is not important when the expression for the transition probability is evaluated. A transition dipole moment with opposite direction would give the same transition probability. The best interpretation of transition dipole moment is the one already given above and repeated here. The perturbation distorts the initial state. This is described by the dipole moment operator, which distorts the initial state psi0 and produces a new perturbed state mu psi0. The transition dipole moment describes how similar the distorted state mu psi0 is to the final state psi1. The more similar it is, the more likely is a transition. When discussing infrared spectroscopy, we will see that the transition dipole moment for infrared absorption has a simple classical analog, the change of dipole moment during the vibration. In contrast, the transition dipole moment for electronic transitions observed in UV visible spectroscopy does not have a classical analog. This makes it a bit hard to illustrate its meaning, and I will discuss it in more detail in the UV visible spectroscopy lecture.